Hello and welcome back to Calculus1. We are starting chapter 3, chapter on derivatives. So this is going to be the second part. Calculus1 is kind of divided into the first part on limits, second part derivatives, and third part integration. So we are starting this middle part on derivatives, and we're going to talk about the limit definition to the derivative today, and do some calculations, see the way to derive the derivative from algebra and other things that you already know. So where do we start? Well, first off, I'm just going to say real quick that the derivative measures the change. Derivative measures the change. You can detect the growth of the plant or a growth of a human or whatever using the derivative. Even the subtle changes. Do you know that you are the tallest when you wake up in the morning? Yeah, you are the tallest when you wake up in the morning because while you were horizontal, your body stretched out, right? Everything relaxed. When you wake up, you get up, that's the tallest you're going to be for that day. And then, as you move around, your body weight is going to slightly compress all of your joints, right? And you have knees and ankles and hips and everything else. And everything will be compressed to a fraction of an inch. And you will be shorter by the end of the day because of all of that. Same goes with body weight for most people. You are the lightest when you wake up and heaviest when you go to sleep. So, and then you have, if you have 8 hours of sleep, then there will be no food for those 8 hours, and you actually use a lot of energy to run. Your body uses a lot of energy to run. Look up that stuff, just to run and sustain you throughout the sleep. So derivative will be used to measure the change, and it doesn't matter if the change is large or small. We can use derivative to measure the change. So now, we would like to derive the formula which measures the change. Now, let's take a look at the picture that we're going to use to derive this. We're going to have some kind of a function, say like that. Sounded like a seal. So we have a function f of x, and we are going to have 2 points, point P and point Q. The way to measure the change between points P and point Q is to connect those 2 points with a linear line segment PQ, and that line is called the secant line. Secant is in Greek means to cut. So you can see that this blue line cuts through the function, and we call this line secant line. What we are going to do now is we are going to let this Q move on x-axis. As it moves to the left, the Q will start approaching P. Now, over here, Q has the x value and P has the a value. So you see that x goes to a. X goes to a. Now, point P is fixed point. Maybe I can write that here, fixed point. So since P is fixed and Q moves, P gets to send these lines like that, all of these different secant lines to meet each of these points. So that's Q, Q1, Q2, Q3, right, going all the way around. Now, what are the coordinates for point Q? Where clearly they are x and y, or x and f of x, whatever. And the point P has coordinates a, f of a. Let's call this x, f of x. So it's consistent with a, f of a. And if you want to compute the slope of the line, you will use the slope formula. And that formula is easy, right? Because you learned that in algebra. So slope of the secant line is going to be f of x minus f of a divided by x minus a. That's your good old y1 minus y2 divided by x1 minus x2. You know to do this, right? Because that's basic algebra. Now, this particular secant line is the way to use algebra to measure the change. What kind of change am I measuring? Well, please think of, I'm going to erase this. Consider this triangle here. And as you are considering this triangle, understand that there is change in x, which we usually call delta x. So change in x to go between x and a. And then there is also a change in y, which is the height change, because clearly point Q is higher than the point P. So there is a change, there is a location, right? They're in different locations, so there is a change between them. So now I can measure that change by dividing your delta y, which is change in y, by delta x. That's what the slope of the line is. And the slope of the line measures, you can think also a pitch, right? Like, you angle the roof so that the rain and the snow can fall off into the gutter and be directed away from the house. Or the sidewalk or the road, they should have a pitch to direct the water away from the house or away from the road and so on. So it's angled, right? And if it's angled, the stuff will roll down that way. Water, marbles, and so on. So I'm going to erase this, as I said. So now we have the good old algebra formula y2 minus y1 divided by x2 minus x1. And we just used f of x, f of a, to plug everything in. Actually, you know what? I'm just going to do this. M equals y2 minus y1 over x2 minus x1. And I'm just going to point the arrow down into it. Because we're using the same formula, we're just using the values off of our graph. So it's just a little bit more involved. Now, everything that you see in blue is the snapshot in time. This line is actually not moving, not going anywhere. It's just a snapshot in time because algebra doesn't deal with motion. Algebra just says, oh, there's a line, let me calculate the slope if you give me 2 points. Sure, here's P, here's Q, give me the slope. So that's what we have so far. No motion, nothing happening there. I did use motion to kind of stretch this Q and go through all the iterations, not all the iterations, some iterations where the Q is going to be, but I haven't actually done anything in terms of motion yet. Now I'm going to ask you to imagine this point Q move. As it moves, that was a good one. As it moves, it will keep creating these different lines, and these different lines, the blue lines, each one of those, if you pick any one at random, you can always calculate its slope because you have the algebra formula. What happens when Q finally collides with P? Well, what happens in the denominator in that case? You see, there is an issue there, right? Because our denominator was always x minus a, because x and a were different values on x-axis for all of these blue dots as we go along the function. But eventually, x is going to hit a, and they are both going to be at the same location, which is happening at point P. Do we lose our lines at that point? Well, clearly algebra can't compute it. Because when x and a are at the same point, let's say 3, then 3 minus 3 is 0, and you do not get to calculate the slope of the line that way. But if you are following the trend of these lines, you see that these lines are pointing towards a special line that exists at this point. It's only one of them that exists at that point, because as soon as Q passes P, it will start spawning blue lines again. The only issue that we have is at point P, where x and a are the same value. So that's a very special place. And you see that there is a line there. Can we compute that line using algebra? No, because the denominator is 0, and we can't calculate with denominator being 0. So is there a way to compute that line? And then also, what does that line represent? Why do we bother? Well, turns out that red line is the reason why we have technology today. As simple as that. All of it. All of it. Anything you can think of. Prior to that red line, our species used to hit 2 rocks to make fire. And then the red line came about and spawned everything. Right? Wow. What a line, huh? It's like, really? Everything? Everything. Everything. That line is called the tangent line, and eventually we'll learn that the slope of that line is the derivative, which measures the change. Now, what is a change? We will learn that change in position in time is velocity. The change of velocity in time is acceleration. The change of acceleration in time is jerk. We're going to learn that we can calculate the change in population for bio majors. We can calculate the change in electric field, change in magnetic field, change in gravitational field. We can find a whole bunch of stuff. Change. There's a lot of stuff that evolves and changes in the world around us, and everything, every single concept, if it's changing, is explained by the red line. If it's not changing, it's constant, it's not interesting, you observed it, it's not going to go anywhere, don't worry about it, right? But when you take a look at those stock graphs, right, going up and down and up and down and up and down, right? Heart attack induced, that's why they look like that, right? Looks like the heart attack thing, right? Going on. You never made that connection? Now you do, right? You smooth that out with a line, with a straight line, and you say the money is growing in time, we're losing the money in time, buy, or sell, right? Well, the people used to do that, now AI does that, but someone had to program it in, right? So this red line is a very special line, one of a kind per point. And as you can see, the blue line was adjusting to connect P and Q at all times, and then eventually P hit Q, denominator became 0, but we still have a line there. And then when Q passes, we're still going to have blue lines spawning on the other side. So, what is so interesting about this red line? Well, all of the infinity of blue lines that you can draw on both sides, right, point P, all of them can be computed using algebra, because you will always have x minus a to be different numbers, x and a, and you will always have some difference in denominator, and you will be able to use algebra to compute the slope. And those are secant slopes. The issue of the red line is you only have 1 point. And because you have 1 point, you cannot compute the slope of that line using the slope formula from algebra. But do not despair, because it can be done. What kind of a behavior you see as these blue lines move that way? What is the behavior? What is the red line? The red line is, yes, the red line is the limit of all blue lines. As the blue lines move to the left, their final destination is the red. They can't go past that. So, to calculate slope of the tangent line, you will say limit as x goes to a of slope of the secant line. And now that would be written as m tangent is equal to the limit x goes to a of f of x minus f of a divided by x minus a. This is the slope of the tangent line and this is what measures the change. You see that that line is angled? It will tell you how much change in y for how much change in x. If you are struggling with the concept of measuring change with a line, let me just draw a picture over here. Let's say you are driving 60 miles per hour. 60 miles per 60 miles per hour can be written as 60 miles divided by 1 hour. This is what you do to write a ratio at which you are driving. So it's change in y divided by change in x. So I can graph that. If I say that this is 60 and this is time, this is 1, you have that, 60 miles per hour. So distance, time, 60 miles per hour. And that's 1. When you're driving 60 miles per hour, you are covering 1 mile per minute, right? Because you have 60 minutes in 1 hour. So if you're driving 60 miles per hour, you are driving 60 miles in 60 minutes. 60 divided by 60 is 1. So you're covering 1 mile per minute. And you can use that to approximate how long will it take you to get place, if you know, get anywhere, if you know how far you have to go. Let's say you live in on 78 exit, 15, exit 15 and exit 26 of RACC are 11 miles apart, because 26 minus 15 is 11. There is an exit every mile. If there is nothing to go to, they just skip the exit. So you have exit 17, you have 15, 17, 18. There is no 19, right? The roads are really organized if you think about it a little bit. And mile markers follow the exits. So the difference on the highway between exit 26 and exit 15 is 11 miles. You cover at 60 miles per hour, you cover 11 miles in 11 minutes. Very simple. And then if you drive a little bit faster, you will cover it a little bit sooner. Now, can you actually save? Can you save 5 minutes on an 11 minutes ride? No, you can't. Because that means that you have to constantly drive 90 or 95. Chances are you're going to get pulled over. And I don't think at that point they will give you a ticket. So, no repeat offenders. RoboCop or Judge? No, Judge Dredd. It's one of them. All right. So we have now the method to measure the change. And you see what the change is. You covered 60 miles in 1 hour. What changed? Everything changed. Because from this point on, 1 hour in time, you're somewhere else. And in 1 hour time, you're 60 miles away from where you have been before. So these things measure the change. And it's clear that we have to use the slope of the line because that's what slopes do. Right? That's what slopes do. They measure the change. Now, there is a big difference between the blue and the red. And I already told you what the difference is, and I'm going to add to it now. The blue ones are the secant line, and you use the basic algebra to calculate because a and x have different values, and you can use basic algebra to calculate slopes of every blue line you want. Red line, special line, called the tangent line, has only 1 point, and because x minus a in this case would create a 0 in denominator, algebra is completely useless to find the slope of the line. But ironically, that's the only point we're interested in. Because what you guys see, I don't know if you can understand it now, but hopefully throughout the time you will. The blue stuff is average. The blue stuff is average because you travel through time and you will travel at different speeds. You know how you drive a little bit and then there's a stop sign and then you stop. And then you drive a little bit more and there's a deer and you hopefully stop as well. And you drive a little bit more and there's another stop sign or traffic light. You drive a little bit more and then you have to slow down because there's a parking lot, right? So you never drive at the same speed. The speed goes up and down, up and down. When you sit in a car, the car is going 0, I hope, right? Because it's not that like car is cruising at 60 miles per hour, you jump in, right? I don't think even the action movies do that anymore, right? No. Car is parked, right? And then you do the usual spiel, right? As a driver, every time you walk around the car, check if everything is okay on the outside. Then you unlock the car, get inside, put your seatbelt first, then you start the car, right? There's a procedure to do these things properly. And when you start driving, you're starting from 0. It takes time to accelerate to 60 miles per hour. Let's say you have Tesla, so it's 2.3 seconds, right? For anything else, it's like a year and a half in comparison to that. So it takes time. The speed goes up and down and up and down and up and down. You're still going to cover whatever amount of miles you have to cover. Let's say you have to cover 30 miles to come here. There are closer colleges, by the way, but we are still the best, so of course you're going to do that. So in those 30 miles you had to cover, the speed went up and down and up and down and up and down. When you calculate the average, You are not going, and someone tells you, how was your trip? Well, you immediately can, start working on some math with this person. Because, how was your trip? What you do is you say, I covered 30 miles, right? I covered 30 miles because that was the difference between the college and your house, let's say. 30 miles in 45 minutes. Now, this is where you take the abacus and you divide, right, to find the speed. Now, obviously, 45 minutes needs to be converted into hours because when we talk miles per hour, not miles per minute. So the first order of business is to multiply by 60 minutes in 1 hour. That will kill the minutes. So you have 30 times 60 divided by 45. Right? And that's... Did we just came up with something that it's... No. 30 miles in 45 minutes. That should be good. So, good. As I foreseen. So, the average speed is 40 miles per hour, right? Did you start at 40 miles per hour? Jumped in a car right into motion? No, you started with 0. On the parking lot, do you kind of roll out a car and let the car drift off? Right? No, right? So there are times when you went less than 40, more than 40, less than 40, more than 40, right? The blue lines average all of that because the blue line has the difference in time and the difference in distance, and it all mushes it together into a single number. And all I know is that since you had to start from 0 speed and you parked the car and it's 0 speed, there have to be instances when you went more than 40 miles per hour, so that you can average those zeros to average and so. But now, what's the red line? So the blue lines are averages. What's the red line? Red line is a very special line because that line measures your velocity right now, this instant. It's called instantaneous velocity. And this is why it's so important. That is your speedometer. You're driving, you look at the rearview mirror, woo, and then you look at the immediately, right? The next thing you look is what the speed is, right? And you find out it's not a speed, it's just your stoplight is out. It's just like, great. So the red line is any instant when you glance at the speedometer, whatever number it reads, that's the red line. Because as you can see, for x-axis, if that is time, your entire trip is between A and X. Your entire trip is between A and X. And that's why the blue line calculates the average. Now, look at the red line. The red line is only at one point in time and the whole graph. And that point in time is A. So, because the point in time is A, this is showing the velocity, the speed of the instant. And that's why your speedometer is a collection. Your speedometer is a collection of all of these red lines, and it immediately adjusts. You touch a gas pedal, little bit, goes up. You touch the brakes, little bit, goes down. And we are going to have a lecture later on in this chapter where we are going to talk about acceleration changing the velocity, velocity changing the position, and you get to go places. So it's not a story of a chicken and an egg. It's just a story of the chicken because the egg came from the chicken, right? No one is going to repeat that? That was disappointing. Okay, fine. Maybe next time. So I hope you understand from this point what is blue and what is red. So we are going to label the blue as average, and the red is going to be the limit of the average. Now, the limit doesn't necessarily mean maximum and minimum. No. Remember what the limit is. Limit is any y value that has to be computed, right? So it's not min, it's not a max, right? That's one of the rare examples where the words in mathematics do not mean the same as the words in everyday conversation. When you tell to me, I'm pushing myself to the limit, well, just raise the limit. What can I say, right? Because obviously it's not working, right? So you have to raise the limit. You also know when you say speed limit 65, what happens at 66? No, I tested that stuff, all right?
There are more suggestions than limits.
So, you see, so the speed limit doesn't mean maximum. If you go to certain states, they have a minimum speed limit of 45, maximum of 75. You go out of that range, you pay the ticket. So you drive 25 on that highway, you are going to get a ticket, right? So you have some highways that have that as a rule. So, or Autobahn in Germany. What's the speed limit?
Just go.
No speed limit.
Just go, man.
There is no speed limit. See, one of my poor friends who moved to Germany worked as a control engineer for air conditioning and for the car companies. So his company was contracted by all of the car manufacturers in Germany to do the quality control and to test air conditioning, right? And he was one of the test engineers. So poor guy had to drive prototype German cars on Autobahn highway from Germany to Italy and back.
Oh.
I mean, it's tough. I mean, you have the next generation Audi S7, and you have to take that car on the road. Then you have the BMW whatever version that is going to be out next year. So they put a little bit different body on it, so it's it's not going to be the new body. He's just testing. Poor thing. It was terrible, right? Because no one limited the speed on the highway. You don't know how fast you can go.
Wait, so is everyone just going super fast over there?
No.
Really? That's so lame.
That's why you don't have it here. Okay? See what you did? See what you did?
So, question about this.
Yes.
So, if you're using this example to measure speed, right? So, from X to A, and if those...
The speed is the division of this because the x-axis is actually time and the y is distance. So, distance divided by time would be the speed.
So, you said that
velocity.
The tangent line is the current speed, right?
Yes, instant.
So, is that only at that point?
Yes, because if I come out to this point here, the tangent line is going to look like that, and the slope of that line, right, it's going to be a number. Slope of that. So the slope of the red line at what I was talking earlier is 60. Slope of that line is 60. so m a value. You know how the equation of the line y equal mx plus b,
Yeah.
it would be y equal 60x plus 3. That 60 is going to be the slope of the red line, and that is the speed. Now we're going to have a lecture on that, right? So there's no reason to stress about it yet. Eventually you will have to stress
Yeah,
it.
I'm just trying to get it straight.
But yeah,
So at that one point, then if it moves, if it moves over from point A to point B, say if it moves one line over,
it's going to be a different line
then you
because
just
there's function.
recalculate, and then you can see what.
Recalculate everything, yes. Well, now we're going to do examples for this stuff. So the blue stuff is the average, which is algebra. The red stuff is calculus. We use the limit, and we have the formula now down below. Now, we really don't want to compute this formula, right? Can we make this easier? And the answer is yes, we can, right? So let's make this easier. So I have the formula which says the limit x goes to a of f of x minus f of a over x minus a. And we would like to make this formula easier. So what I'm going to do now is I'm going to define the letter h to be x minus a. Cool? Of course, math, right? So what I'm going to do now is I'm going to subtract a over here on the limit, and I'm going to have limit x minus a goes to 0 because a minus a is 0 on this side. And then over here, I'm going to have f of x. When I solve this for x, I get that x is equal to a plus h. So when I plug that in the first one, I get f of x a plus h minus f of a, and then I have x minus a over here. So now we already have that x minus a is h, and we get limit h goes to 0 of f of a plus h minus f of a divided by h. Just a little bit of mathematical gymnastics there to do this derivation. Does this look like something?
Difference quotient.
Difference quotient, yes. So now, there's the difference quotient we talked about the first day, difference quotient that you learned in Pre-Calc 1, and maybe your teacher did not tell you anything about it and why you have homework assignment on it. Now, we get to compute difference quotient so that we can compute the derivative, and derivative is telling us the change. So we need that thing, right? Easy.
I'm gonna scare you.
No, I thought you got excited because of the derivative. So this thing is going to give you the slope of the tangent line. And we're going to box this. We're going to have one more iteration of this formula, so don't go crazy on a box, okay? Let's do an example since we've been talking theory for the entire lecture so far. So how about if I say that I would like to calculate the slope of the line for the function so-and-so at the point so-and-so. So let's go. Find the slope of the tangent line at x equals to, say, 3 for the function f of x equals x squared minus 2. So find the slope of the tangent line at x equals to 3 for f of x equals x squared minus 2. Well, the most important part, and please pay attention to this and label it 1,000 times if you need to, This is your A. Everything happens at x equals A. So A is either written as a parameter, which means it takes particular value, or it's written as x equals to, let's say, 3 in this case, in which case your A is 3. What A? The A from the formula. So now we are supposed to work out all of these parts individually and then stuff them into the formula and compute the limit. Guys, this problem is from 2.3. We did this in class. I remember working out 1 over x in class for difference quotient, and we had the limit in front. And we got the answer of negative 1 over x squared. You can go and look at your notes. If you took the notes, you can look at the notes and you will find the example when we did the difference quotient for 1 over x. We are doing now identical, same limit. This can be placed on your first exam. This calculation is 100%. 100% of this calculation is 2.3 limit. That's all. What's 3.1? The name I'm going to give it, which is slope of the tangent line. So I'm giving it a concept of the calculation which you guys learned first in pre-calc and then in 2.3. So here we go. What are my ingredients for this soup that we are making? Well, I need f of a. F of a is actually our f of 3. So f of 3 is 3 squared minus 2, which is 9 minus 2, which is 7. Another ingredient for my soup is f of a plus h. Well, that is going to be f of 3 plus h. Okay, that's going to be 3 plus h, everything squared, minus 2. So now you have to square it and work it out. So 3 squared is 9, plus 6h, that's your middle term, and that's what your grade usually does, plus h squared minus 2. So this one is equal to 7 plus 6h plus h squared. Good. Now, to calculate the slope of the tangent line, we are going to calculate the limit as h goes to 0 of f of x plus h is this mess. You Control C, Control V into the formula. So 7 plus 6h plus h squared minus f of a. F of a is f of 3. F of 3 is 7 divided by h. 7 will cancel 7. And you see that you can kick out h. So limit h goes to 0. You kick out h, and you are left with 6 plus h divided by h. This is where h cancels with h, and you have the limit h goes to 0 of 6 plus h. What is the limit as h goes to 0? 6. Good. So we found out that the slope of the tangent line is 6. That's the change, right? 6 of something in 1 of something. 6 miles per gallon. Let's say you're driving a truck. 6 miles to a gallon, right? They're usually 15, 17, 19, right? You have one of those pickup trucks. They're usually like by 18, 15 to 18. Good. So we calculated slope of the tangent line, and this 6 is measuring change in an instant. What can this represent? The number of new bacteria that we got within the last minute. Okay, fine, right? The number of leaves that fell off the tree in the last second. Maybe you are talking about 6 million. The population added to the planet within whatever time frame that happens in, right? It calculates the change, but it calculates the change of an instant. You might be walking 6 miles, well, it's running, right? 6 miles per hour. And that's your current speed. You know, you can go on a treadmill and make it to go 6 miles per hour, and then you run. I don't know why I would do that, but let's say you would, right? And you do that, and you run. Yeah, it's a funny concept. There's nothing chasing you, and you get nowhere because you're running in a spot, right? Isn't it right?
No, you're right.
Of course I'm wrong. Just observe people running on a treadmill. It's comical. They're getting nowhere, and they still run. They waste all of those calories that they hate. Just don't eat the calories then. Why? Eat so you can waste them. I don't understand. Like if you are a mailman and decide not to drive but run from house to house and deliver mail, you at least achieved something, right? In addition to whatever. Okay, so we calculated for this function here, find the slope of the tangent line for this function, and we got it that at value 3, slope is 6. Now, as it happens, let's say you're working at a corporate, this was assigned to you to calculate by your boss, right? And then you came back from the, right, you handed this in, went to a break, come back from a break, and the boss goes, it was not x equals 3. I read it wrong. It was supposed to say x equals 8. Oh, great. Now I got to do everything again. Let's go. So f of x is equal to x squared minus 2. That's our function. And x equals 8. Because 8 kind of looks like as a half of 3. I mean, 3 is like a half of 8, right? You see, if you write the other 3 on the other side, it looks like 8 now. So it's a common mistake in corporate. Now you got to do the whole thing again.
That's fine.
Let's go. F of 8 is 64 minus 2, which is 62. F of 8 plus h is going to be 8 plus h squared minus 2, which is going to be 64 plus 16h plus h squared minus 2 for a total of 62 plus 16h plus h squared. M tangent, look at that productivity, huh? Working towards your bonus. Limit, h goes to 0. We have 62 plus 16h plus h squared minus 62 divided by h. So in here, you have your f of a plus h minus f of a, and you have h on the bottom. So all of the ingredients of our formula are there. Now we compute this real quick. We have the limit. H goes to 0. 62 and 62 cancels. At this point, you factor out h. You get 16 plus h divided by h. You cancel h and h. You get the limit. H goes to 0 of 16 plus h. And as h goes to 0, the slope is 16. M tangent equals to 16. Print that out, put in a report. I have it for x equals 8. Excellent. All I need now is for x equals negative 3, x equals 25, and x equals 100. What are the slopes of the tangent line there? That's going to be 3 separate calculations. Every time is the same calculation. And you have to start from scratch, because as soon as you introduce a different number for a, all of this stuff changes. And then in the formula changes here to calculate the value you want at the end.
So instead of, trying to factor it or trying to, compute it for f of a, what if you do it for just f of x or the whole formula?
That's it. Beautiful. This is where you go frustrated and you say f of a, which is one of these numbers at a time. Nah. I'm going to put f of x in because that is going to be the variable, and when I compute this thing for x, I can plug any value I want in the final answer, and that will generate all of the values I want. So what you are doing now is you're hacking this formula. Limit h goes to 0 of f of x plus h minus f of x divided by h. And this is now your new formula for when tangent. And then later you get to figure out which numbers you're going to plug in. So now, if my f of x is given as x squared minus 2, I compute f of x plus h in general terms, which is x plus h squared minus 2, which gives me x squared plus 2xh plus h squared minus 2. Plug this thing over here, plug this thing over there, and work out the limit. So m tangent is going to be given by the limit h goes to 0. Now I have my f of x plus h as x squared plus 2xh plus h squared minus 2 minus the x squared minus 2 original function divided by h. X squared minus x squared cancels. Negative 2 and positive 2 cancels. And that's a positive 2 because this negative distributes inside. So what you are left with is the limit h goes to 0 of 2xh plus h squared divided by h. What should I do? Kick the h out. Very good. Kick the h, you get 2x plus h divided by h. Cancel the h, and you get a limit h goes to 0 of 2x plus h. When h goes to 0, the answer is 2x. Now, the boss said negative 3, 25, and 100. X equals negative 3 will produce the slope of negative 6. X of 25 will produce the slope of 50. And x of 100 will produce the slope of 200. What you did is you computed the function which generates all slopes of all tangent lines when you provide me with the function and you provide me with the point where you want to look at. So this function here generates all slopes, or all tangent line slopes, all tangent line slopes for given f of x. You change f of x, that calculation changes, obviously. But if you have one function and you want to calculate 4 or 5 different locations for the tangent line, the best bet is to compute the limit for the difference quotient limit, right? For the whole thing, and get this function which will generate the slopes. What was our first problem? Our first value? X equals 3. What was the answer? 6. What was the second value? 8. What was the answer? 16. Why? 2 times 3 is 6. 2 times 8 is 16. Because this function is the one that will give you all of the slopes. Now, remember the problem, if you flip your notebooks back and you looked at that 1 over x problem we had? If you have a 1 over x, then let's say you were interested in the slope at 4. What is the slope at 4? Well, the function at the end was negative 1 over x squared. If your x is 4, it's negative 1 over 16. And you have the slope of negative 1 over 16. You know what I'm going to do now with this? I'm just going to slap a label on it. And the label is the name for this function. What's the label?
Difference quotient.
That's the formula we use to get it. What's the name for this function? The derivative. that's the label. Right? So the calculation is 2.3. This problem, so now I get to ask you, do you want this problem on a test? And you say, no, that's chapter 3. We're not going to have the new material because it's confusing. Oh, really? This was a 2.3 calculation. I ask you this question, but I say compute the limit. Then you say, yeah, sure, add this to the test because it's the same as 2.3. Then I say calculate the derivative, and I give you the same problem. So whether you want it or you don't want it, it's going to be there because it's 2.3. What's 3.1? Me slapping the label and calling it derivative. That's the only thing we did now. All right? The whole thing is just calling it derivative. Go back in 2.3, find these homework problems. I told you had 5 of them in the book, right? So this function that in the end computes all of the slopes is called the derivative. So now I get to write this final formula using the notation for the derivative of the function. I'm going to say that the derivative of the function f of x, which is denoted as f prime of x, the derivative of the function f of x is given by the limit h goes to 0 of f of x plus h minus f of x divided by h. That is the derivative. This is the one that gets the box, and this is one of the most important formulas of Calculus 1 and one of the biggest focus points of Calculus 1. It measures the change. This is a difference quotient, but we have seen that this is actually your basic slope of the line modified, and we call this the derivative of function f of x. The next section is going to introduce graphing, and we're going to see how these two work together. I just want to add, because we actually did not compute the equation of the tangent line. All we computed so far was the slope of the tangent line only. The derivative only gives you the slope. It doesn't give you the y-intercept, which is the b part in the y equal mx plus b. So we have a little bit more work to do to get to the full tangent line problem. So what I'm going to do is I'm going to come up with, I just want to jump into the homework section and work out one more problem, but this time I want to find the entire tangent line for the problem. So let's go with problem. Oh, this addition is not the same as your addition, so I'm just going to put the random problem. Find tangent line for f of x equals square root of x minus 1 at x equals to 2. Now, just in case we are not going to calculate this at 2 directly, we're just going to calculate the general derivative because we never know when they might change the mind, right, from 2 to any other number. So let's just do this in general terms. We're going to find the derivative using our derivative formula. So f of x plus h is the first thing we have to figure out, and that's simply f of x plus h minus 1. You replace your x with x plus h under the root. And now we come up with our derivative formula, which is going to be the limit h goes to 0, and now we have our square root of x plus h minus 1 minus the square root of x minus 1, everything divided by h. What do we do here? Well, the only thing you can do is what? You have square roots. Can't square because I only have one expression. Rationalize. That's why I go rrr. You rationalize by multiplying this expression, square root of x plus h minus 1 plus root x minus 1 over root x plus h minus 1 plus root x minus. So this orange expression is 1 because you're dividing the same values. And you have the, now we're going to multiply. Do not multiply in denominator. You just multiply in the numerator. So what I have is the limit h goes to 0. When I multiply on top, square root times the square root will give you the quantity underneath square, and square kills the root. So you get x plus h minus 1. And then you have a minus over here. The middle terms will cancel, and you have x minus 1 in the parenthesis, divided by the h times square root of x plus h minus 1 plus square root of x minus 1. In the numerator, as you can see, x minus x is gone, and negative 1 and a positive 1 are gone. This minus will distribute, changing into a plus, right? So everything is canceled there, and you are getting the limit h goes to 0 of h divided by h times the square root of x plus h minus 1 plus square root of x minus 1. Cancel the h, and what happens as h goes to 0? You will have 1 divided by 2 square roots of x minus 1. Because when h goes to 0 over here, the 2 square roots are the same, So square root plus itself is 2 of them. Apple plus apple is 2 apples, right? So 1 over 2 square root of x minus 1. What you found is that the derivative is 1 over 2 square root of x minus 1. Now we use the value provided. In the problem we were given x equals 2, and this is where you calculate your slope of the tangent line, 1 over 2 square root of 2 minus 1. And that is 1 over 2 square root of 1, which is 1/2.
How'd you get rid of the h?
H goes to 0 in the limit. So you literally just get rid of it. Right? You literally just kill it. Because limit sends h to 0. Limit doesn't bother x's. Limit has nothing to do with x. Limit operates on age in these problems. So every age goes to 0. And that's the reason why we had to cancel this. Because if you don't cancel this, the denominator age is 0 and we can't compute. But once you start doing the derivative correctly, all these calculations correctly, that age in the denominator will always cancel, and you will be able to solve the problem. So once you are at this point where there is no more age in denominator because it canceled over here, you will still have the age here, but that age goes to 0. So when that age goes to 0, I just have square root of x minus 1 plus square root of x minus 1, which gives me 2. Right? I mean, you can rewatch the video. If you put the sub notification bell on, right, you'll be alerted of this episode, and then you can rewatch it a few times. Right? It's just Shaolin algebra at this point. All right, guys. So what do I have? I have a function f of x, which is given as a square root of x minus 1. I have a point x, which is 2, and I have slope of 1/2. We know that y is f of x, and in our case, I need to calculate f of 2. So that's going to be a square root of 2 minus 1, which is 1. And the specs for the line are 2, 1, and the slope of 1/2. Now we are getting into algebra mode to calculate the tangent line. How do we do it? Well, you can go the y equal mx plus b route, or if you like paying y minus y1 equals to mx minus x1. I don't care which one you use, whatever. Generally, I always use this one because, I don't know. Y is equal to 1, slope m is 1/2, x is 2 plus b. 1 is equal to, this cancels, 1 plus b, b equals to 0. Tangent line is at y equals 1/2 x plus 0. That's the tangent line for this function at 2. Now let's say you care, right, and you want to check this. The way to do that would be to just simply graph these two functions and see if they touch at 2, 1. So you are going to go to Desmos, let's say, or whatever graphing thing. You can also use your graphing calculators. You can put the graphing app on the phone. And you will graph two functions on the same plane. We have we have a square root. So open parenthesis x minus 1 close parenthesis, caret 0.5. So that's the square root function shifted at 1. And then I have y equals 1/2, so 0.5x.
You can still do the square root thing.
Yeah. You can write it, SQRT, right? And yeah. So the blue line is the tangent line. The red line is your square root line. And where do they touch? At 2, 1. Now, what is the meaning of the tangent line? Tangent line is a linear line. And in mathematics, we say it kisses the function. Why do we say kisses the function? Because there's one mouth and you can just achieve one kiss, right, at one location, one time. So, this tangent line is not going to bend back and meet this function again. It could happen if the function is a sine function and you go with a tangent line on top, sine function is going to keep hitting that tangent line, right? Fine. But in this particular case, and many others, right, it's not going to bend back and meet it again. So you see over here at 2, 1, this is where they touch, and it's the only point that they share. Also, to understand the tangent line in the other sense is tangent line, right, the blue line, is always perpendicular to the curvature that it touches. Now that's a little bit harder concept to understand, but generally, you see, there is curvature, right? There are curves here. What you do is you take a small piece around where they touch, and that small piece is going to have some curvature to it. That curvature changes as you go away. But for that little piece around where they touch, you can draw a huge circle so that the curvature of the circle matches that little bit of a curvature you had. When you draw the line from the point of intersection to the center of the circle, that radius will always be perpendicular to the blue line. And that concept is very important for physics, for kinematics, for a lot of concepts, because eventually I will talk about the car that slips on the curve. So you have a curved road, and you have a car. Those are the tires, and the exhaust with a right? You know, one of those cars you go brrr, and it's like $20 of gas, right there. As you drive, let's make it a truck. As you drive, right, are going to be leaves and oil and water here.
It's like Mario Kart.
So, Luigi. All right. So at this point, when tires lose the grip with the road, right? Friction is a good thing, otherwise no cars, right? Not always the good thing. In this case, the good thing, right? When the tires lose the grip with the road, right there, you see this curve? That point has a tangent. That's the way the truck goes. Okay? That's the way the truck goes. Off the road, tangential to the curvature of the curve. Which is why you either brake before the curve, or you accelerate out of the curve, or both. You do not drive 45 miles per hour into the curve without doing one or the other. You are going to be in trouble every time, right? So that's something that is basic physics, but the motion, which way the car or truck or whatever goes, is going to be tangential. Another example of this would be those ancient weapons when they take a piece of wine, no rope at that time, and you put a stone at the end, and then you swing it like this, right? And when you swing it, you let go. Now, this is going to go around, and if I want to toss forward, when do I release? When do I release?
The moment it's pointed at the direction you want it to go.
No, definitely not. Because this is going to go tangential. If I'm trying to hit him, and I let go when this looks at him, it's going to go that way. It has to be here. When I let go, it's going to go tangential. Dinner for me. So, when you do that, now it's obviously, this is applied class, so you should go home, take a piece of rope, take a stone, find a tree, or if you don't like your neighbor or something, right? And go swinging, right? Figure out which way it goes, right? If you're a klutz, wear a helmet. Seen so many people. It's like, oh, look, I bought a nunchak, right? Good for you. Please record everything you do, all right? So that's that, guys. That's the introduction to derivative. Derivative is simply a function that generates all of the slopes of the tangent line for a given f of x, and then you can compute all of the tangent lines which have a lot of application and basically drive everything we have today in terms of technology and things we have built. Bye.
That's cool.